Hi, welcome to Couchbase Online. Today we're going to talk about choosing a database in the microservices world. Come join us. Databases in the microservices world. Here's the point where I tell you I'm definitely going to post the slides on my site tonight. You're going to go check tonight, tomorrow, next week, next month. In about 3 months, you're going to get tired of waiting and you're going to email me. And in about 6 months, I'll reply and say, no, I'm definitely going to post them on my site tonight. And I'll never post them at all. I've been that person and I don't like it at all. So you'll see that the slides are online right now at robrich.org. Head over to robrich.org, click on presentations, and up here at the top of the list is choosing a database with databases in the microservices world. While you're here on my site, come to the About Me page, and you'll see this content, which talks a little bit about things that I've done recently. I'm a Microsoft MVP. I'm a friend of Redgate. AZ GiveCamp is wonderful. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. It is a lot of fun. Or if you'd like a GiveCamp in your area, hit me up by email or on Twitter, and let's get philanthropy installed in your network, in your neighborhood too. Some of the other things that I've done, SQL Source Control Basics, minus Chapter 8, that was a lot of fun to build. Some of the other things, one of the things I'm most proud of, I replied to a .NET Rocks podcast episode. They read my comment on the air. They sent me a mug. Woohoo! So there's my claim to fame, is my coveted .NET Rocks mug. Okay, so let's dig into databases in the microservices world. We talked about this guy. Application architecture. Well, how did we get here? Well, we've been on this journey from Monolith to microservices, and I really like this description of the problem. This came from this blog post. It's really cool. As you grab the slides from robrich.org, come click on these blue links and go exactly there. He talks about going from spaghetti architecture to lasagna architecture, N tier, to ravioli architecture or microservices. And it's really cool. Looking at it a little bit differently, we used to build monoliths like this on the left. And now we've kind of moved towards microservices here on the right. Well, why did we choose monoliths? Well, we chose monoliths because deployment was hard, and it was difficult for us to get all of our content into production. And because it was so hard, we chose to not do it very frequently. Maybe deploy once every 6 months or once every year. We'll all get together on a conference call and we'll start the deployment Friday right after work and we'll just go straight. Sometime Sunday afternoon, we will have figured out all of the bugs and then we all get to hang up and go to sleep. Right up until users start calling Monday morning. So monoliths were perfect in that deployment was hard, so we did that as infrequently as possible so we could be as productive as possible. As deployment got easier with containers and microservices, we moved more towards a microservice architecture where each of the microservices could get easily replaced. Its purpose was to do one small job and to call other microservices to accomplish the task that they do. So we moved from monolithic to microservices because deployment wasn't hard. Well, now that we're in microservices, now what? And that's what we'll dig into. Which databases do I choose now that I'm in microservices? As we get to microservices, one of the things that we look at is each microservice does one small job. It's easily replaced, and it can be deployed independently. Well, and also, it owns its own data. It owns its own data, so that at that point, then we don't have to go touring through the building. Hey, who's the one who owns this column in this table, or can I delete this column, or is this column even used anymore? All of that goes away when a microservice owns its own database. Can I get rid of it? Well, this app isn't using it. Yes, of course we can get rid of it. And that's one of the core principles of microservices that make it so powerful. A microservice owns its own data. Well, but usually when we start moving to microservices, we don't get to the spot where it owns its own data. We get to a spot like this. Now, why is this? Why do we spend so much time getting all of our applications refactored into microservices only to turn around and use one big monolithic database? Well, there's a couple of arguments here. Provisioning databases is hard. Yeah, it's getting easier with containers, but it's still more involved because we have stateful resources. We can't just drop the entire web server container and spin up a new web server container with the database because users get a little grumpy when we destroy their data. Oftentimes, knowing that provisioning databases is hard, the DBA will just flat out say no. This is the database that we use, and we only use this database, and you can't do anything else. Yeah, they're trying to protect the safety of the system. DBAs are incentivized by uptime. And that's interesting, but developers are incentivized by deploying new features to users. These tend to be in conflict. Well, kind of. The goal is to keep uptime, to keep safety, to keep to keep customer data safe. And both developers and DBAs focus on this problem. At the point where we focus there, then we can probably get through the DBA said no hurdle. One of the things that's much more prevalent here is that when we have lots of little databases, it's really easy to accidentally miss some configuration. Are we still using the root account with no password, the one that we used in development? Have we secured all the IP addresses associated with access to this database? Have we subscribed this database into backup and retention policies? I've been on more than one project where we get to a certain point and one of those micro databases goes away and it's like, well, hey, let's go restore that from backup. Backup? What do you mean by this backup thing? So, yeah, we need to get all of these databases to authenticate properly, and we need to get them backed up. And those are probably the biggest reasons why we're sticking with the big monolithic database. But let's argue that we don't need to. So if we must have a big database, one big database, we can start kind of logically carving it up into small pieces so that when we get to small databases that we can move in seamlessly. We can create a bounded context. A bounded context is the portion of the database relevant to a particular task. So, for example, if we have a shopping cart site, well, what tables are related to shopping cart? Well, we need the product catalog, definitely. We probably need the orders. The shopping cart experience is going to write to the orders. It's not going to write to the product catalog, though. So the bounded context for the shopping cart probably encompasses those two things. The order details, orders placed, and the product catalog. That's it. We don't need a whole lot of details around user authentication and all those pieces. Those can be handled by the user authentication microservice. And we also don't need a whole lot of detail around shipping address. Those can be handled by the shipping service once they've chosen to check out with their shopping cart. By comparison, the fulfillment center has a very different bounded context. In the fulfillment center, they don't need the flowery description. They don't need all the product images. All they need is the contents of the order and the shipping address. That's it. They pack the box, they mark the order as in process, and away it goes. That's it. The bounded context around the fulfillment service is specific to order line items and warehouse inventory. Those two different bounded contexts could be different structures in our code, both relating to the same database for now if we have a monolithic database. And when we get to smaller databases, then each of those can become their own database. That's pretty cool. We've kind of started practicing of how to get there. And now I'll coin the term micro databases. We have microservices. Let's create micro databases. This micro database is the data store for a microservice. So I'll have one microservice that may have one, maybe none, maybe a few micro databases that it owns. These micro databases serve to do exactly that. So we have these various microservices, and they'll call each other to do the jobs that they need to do. And each microservice will own its own data. Each of these databases then here at the bottom are micro databases. That's really cool. We have microservices for data. Well, what's really interesting here is now that each of these micro databases are separate. So they don't all need to be the same kind of database. That's really cool. Now we can pick the data store that is most appropriate for that microservice. Each of these micro databases now can be tuned to the problem that it seeks to solve. Micro databases. Each one is owned by one microservice, and the other services call into this microservice to get at the data that it owns. They don't go directly to the other guy's database. Rather, they pull in the data by calling the REST methods or the GraphQL methods or the protobuf methods on this microservice. Well, kind of. So how do we do joins in the world of micro databases? If I can't get at your data except for through your API, how do I join your database to my database? How do I get all of the customer's contact info for each order in my order list? Well, that's where something really interesting comes in. We can do this with event sourcing. In event sourcing, we have a mechanism for pushing the data from one microservice across an enterprise service bus into other microservices. So perhaps the order processing microservice publishes events into Kafka. And those events can contain all the details that we need to. The other services that need to know about new orders can subscribe to that Kafka topic and populate their own databases. When the time comes to join, we now have all of the data in our database, and we don't need to reach out into the other database. Now, we don't need to keep all the data. It's not like we have to drink from the fire hose continuously, but we can grab those portions of the Kafka stream that are relevant and save those into our own database. Now we've done joins. Another one, so who owns the customer record? In this scenario of micro databases, in our shopping cart example, well, who owns the customer record? Should the shopping cart, I'm placing orders for a particular customer. Should billing, they're the ones that'll have credit card details. Should human resources? Human resources likes to keep their data very close at hand. And so maybe they should own all of the identity information for everybody. Or maybe sales, they're the ones that first saw the customer. But with sales, there's a difference between a prospect or a lead and a customer. For a prospect, I may only have a first name and a phone number. Or maybe I only have a business card, so I've only snapped the specific things. But to place an order, I need a shipping address. That may or may not be on their business card. That may or may not be on my phone message. So now we have different rules of validation for different types of customer. So who owns the customer record? Ideally, none of them. Let's create a new microservice called the customer microservice that is responsible for the uniqueness of the customer ID. The account number. Now it keeps the primary key of the customer ID, it keeps the account number, and it makes sure that they're unique. And that's all that it has in the customer record. In the shopping cart, they may only identify the customer ID that this order is for. In the billing system, they may dig into a whole lot more. They'll foreign key off to the customer service, and they'll keep additional information like the credit card details. For human resources, yeah, they'll foreign key off to the customer's account number or the customer ID, but all of the data, all of that sensitive data is specific to this human resources system. And we can go through each of these things. That customer microservice only has that unique primary key and the account number. all the other details are in different bounded contexts in different microdatabases. That's perfect. Through event sourcing and through creative use of these microservices, we can get to the point where each microservice owns its own data in its microdatabase. That's really cool. So now we have these microdatabases. Each microservice owns its own data, and the databases don't need to be the same kind anymore. We don't need to have all one type of database. Instead, we can choose the database that best solves the problem. That's perfect. So, because they don't all have to be the same database, they don't all have to be the same database vendor or even database type. That monolithic database that we used before, we probably always used that database because it was, well, the only choice that we had. Now that we have more choices, then the next magic question is, so which one do I choose? And they don't all have to be the same type of database vendor or database type. Said me. Right now. Okay, so now that we get to choose different database types to solve different problems, let's look at the various database types and when they best fit for particular problems. We can then choose the database type that is the most applicable to our problem and start to intermingle the different database types so that we get a much richer experience. We'll look through relational databases, document databases, graph databases, key value, time series, search, object or blob databases, column store, and NewSQL, which may be a new topic for you. That'll be a lot of fun. Let's dig into each one. With each one, we're going to take a look at the characteristics that is inherent in this database solution, the pros and cons, best use cases, and some example vendors. I'm definitely not here to pitch a particular vendor. I understand we're at a database conference, but ultimately, hopefully I'll empower you to choose the right database that meets your needs. So let's dig in. First off, relational database. This is probably the default big monolithic database that you have. For good or ill, we can think of this kind of like Excel spreadsheets. We have an Excel spreadsheet, and in our spreadsheet, we have various columns that identify different types of data. Now, each column has to be the same type all the way through that column, and each row represents one thing. In time, we may choose to split out these into other tables, so maybe we have an order header table and an order line item table. Or maybe we have a customer table and a contact info table. Now, this kind of normalization allows us to create nested data within our transactional database. Some of the things that are characteristic of a relational database, it has those rows and columns. It's also generally one big server. Relational databases were built in the time before we had multi-threaded or multi-processor CPUs or networked machines. So most SQL databases are just one big box. We have tables of consistent rows and columns, and we have SQL queries. Here's a SQL query that kind of is English-like. So we can say, hey, go select this data from this table. We may give it filter clauses, where clauses to say, and this data must conform to this pattern. One of the primary things that characterizes relational databases is ACID compliance. When we look at ACID compliance, atomic, consistent, isolated, durable, by the time the transaction is done, we know that that data is safe in the database. Or if the transaction doesn't complete, we know that that data is not in the database. It will definitely either fail or succeed completely. By comparison, we might have eventual consistency. With eventual consistency, eventually we'll figure out that it's okay, but if I write and then immediately read, I may get the old data. That's by design. That's one of the trade-offs that we get for speed, but eventual consistency versus ACID compliance. Which ones do we need? Well, eventual consistency, when we look at this metaphor, we can look to things like our credit card statements. It'll come at the end of the month, and these are all of the transactions that are all the way done, posted. Well, what does it take to get posted? What's the difference in between there? If I go check my account balance shortly after I make a purchase, maybe it'll be there, maybe it won't. But by the time my statement comes, it will definitely be right. Eventually, it will be consistent. So do you need ACID compliance? Well, maybe. Maybe not. But relational databases usually do ACID compliance. That's one of the things that they focus on. So we looked at relational databases. Pros, we have a strong schema. Table joins. It's a very optimized engine. It's been optimized and tuned for decades. And so this query syntax, the SQL processing, oftentimes can be very different from the storage. And the SQL processing is really tuned. We've all gotten really good at building SQL engines. The compatible familiar syntax of that SQL. Given SQL, we can probably guess what's going on in our query. Now, we can definitely build some bad SQL queries that are hard to understand, but for the most part, SQL is SQL. On the downside, it's optimized for storage size. We talk about third normal form. Now, storage size is interesting, but storage size is much less of a goal nowadays. When we only had 50 megs of space or 50K of space, then data storage was a real big thing. But now that we have terabytes and gigabytes of space, is optimizing for avoiding redundancy really something we need to optimize for? On the downside, relational databases are really not built to scale. The way that we scale up that one big server is we make the server bigger. Eventually, we may hit the point where I can't buy a big server, or a bigger server isn't cost effective. Because they're built to be monolithic machines, I just need one big server. Now, there are ways to replicate database, but these were kind of add-ons added later, and so it's not really inherent in the way that these systems work. That's okay. Maybe. Or maybe that's a deal breaker, depending on the size of our data. So here's some example SQL engines, and you may choose some of these, or maybe these are the search terms that get you to the database that you really need. Relational databases is probably a good default. It's probably the default that you had when you only had one big monolithic database. So, hey, we're already here. If you do have other needs, you may want to stray farther from that. Let's look at the next one, document databases. We can think of these as NoSQL databases, but for the most part, since the last one was SQL, everything else in this list is technically NoSQL. Kinda. So here's a document database that is very specifically based in JSON. We'll have a collection, instead of a table, that is a bunch of JSON documents. Now, each JSON document can have whatever keys and values that it needs to. We can nest these into nested objects. It is just JSON. Now, we may choose to store these not as text, but as binary, BSON, or however we need to store them. But for the most part, we can look at them as JSON documents. Now, the cool thing is that each JSON document is its own document. So we can nest different properties. We can have different fields in different documents. Each document can have its own unique piece. Is that better? We'll see. What's interesting, though, is because each collection is its own thing and each document can have its own thing, there's no real concept of schema, and there's no real concept of joins. These are definitely optimized for reads, and so we'll probably design our application to store the data in the best way to read it. Document databases generally favor eventual consistency over ACID compliance. So that's one of the characteristics here. On the upside, it's distributed, so we'll have lots of commodity hardware plugging this together. There's no schema, so there's no need to do database migrations, and we can have different documents with different content. It's denormalized, so we'll probably have all of our nested things right there in that document. On the downside, denormalized means data duplication. When we're doing updates, we've intentionally chosen to make the updates take longer so that the reads can be faster. we may need to update more than one place to be able to get an update fully in place. Probably because this isn't SQL, we'll need an SDK for each language. We'll have a client library in Node, and we'll have one in Java, and we'll have one in C#, and we'll have one in Python, because these are kind of syntax independent things. Now, we may choose to bolt a SQL-like experience over the top of our document database, but for the most part, now we need to do wacky things like, well, how do I where into an object, into an array where the key may or may not exist? Those are things that normal SQL doesn't need to do. So the SQL associated with NoSQL databases is a little weird. So we end up with unique SDKs for each language. There's no transactions because of eventual consistency. There's no joins between collections. Well, kind of we could do joins if I grab a particular thing and then do a second query into the other collection. It's probably what they're doing behind the scenes if they're supporting joins. Because I have no schema, well, I have to make a lot of assumptions in the application. My app probably has a schema. I assume that this is the layout of the data. But now my app has to be a whole lot more forgiving if the shape of the data that I got back isn't that. So I'll have to do a whole lot of, well, here's the default value if that field was missing or blank. And so I didn't need to define the schema up front, but I kind of now need to compensate for the fact that I don't have a schema. Okay. Maybe as I'm iterating quickly, not having a schema can be really helpful because I don't need to modify it in both places. But once I get to a point of stability, not having a schema can kind of kick your butt. So here's some examples of some NoSQL databases. Couchbase is definitely a NoSQL database and fits really nicely in here. When would I use a NoSQL database? They're great when I need to grab the entire thing. So for example, if I have a news site or a product catalog, I need to load the entire news article together with the author information, maybe the first few comments. I need to load all of the pictures and the category and all of the pieces associated with that article. I don't want to have to do a whole lot of joins to reconstruct this object. I want to just go grab that one object. Given the path to that article, let me go get the entirety of the contents of that article. By comparison, now when I'm modifying things, yes, if an author wants to change their name, I do need to go modify all of the articles that that author wrote to change their name. So it is a trade-off. Outside of SQL and NoSQL, here's some more database types. A graph database. Graph databases focus on the relationships between things. So not only do I have elements, nodes, but I also have connections between nodes, and I can store data on those connections. Connections can be directional. And what's really cool here is that we've created this SQL-like optimized for those connections query language that allows us to query these types of relationships. So I have nodes, I have relationships between nodes, and I have data hanging off of both. I can create a query that starts to navigate those relationships to get at friends and friends of friends in a really elegant and easy way. Graph databases. So how is this different from a SQL table with two foreign keys? Well, the query syntax makes it easy. Arguably, yeah, you could kind of create a graph database by having a table that is the relationship, but now to be able to do friends of friends, I have to join through that table 3 times. And that's kind of intense. So graph databases. On the upside, it's really elegant to get those types of relationships. Friends and friends of friends types of relationships are great. On the downside, because we've optimized for that, we have unoptimized for, well, everything else. So we've chosen that relationship as the primary mechanism here. If I have a problem that needs that kind of relationship experience, then a graph database can be perfect. Messaging apps, social networks, maybe a recommendation engine where it's creating the relationships between products. Here's an example of a graph database that'll get you to other graph databases from your search term. Next up, key value databases. Key value databases are great. We have a key, and then we have a big blob of stuff. Well, that stuff could be JSON, or it could be an INI file, it could be configuration data, it could be a cached web page. Ultimately, the format of that blob is irrelevant. And so the blobs can be different between different keys. We'll always read and write by ID, and so once we write by ID, we can quickly read by ID and get that entire blob. We could think of it kind of as a table with a primary key that is unique and a binary blob. So if we think of it that way, well, what's the value of the blob? Anything. We can use JSON to deserialize some blobs, and we could use binary formatter to deserialize other blobs. What we store in this blob is irrelevant. So it is really great for configuration data. It's really great at those get by ID type of experiences. Because we're getting by ID, then it is really fast. We can also store different types of data in different blobs. That's really helpful as well. On the downside, we really can't do any other filters. We can't filter on the data in the blob. Well, kind of. We could get each key, deserialize its contents using whatever mechanism we have, and then create a filter on that content. But that's really slow. We really have to loop through the entire database to make that happen. We might query on a portion of the key, but for the most part, this is a get by ID only type of system. So here's some examples of key value databases that'll help you find others. It's best used for caching or configuration, maybe user session data. That data that where we just need to dump in a whole lot of stuff, and we're definitely going to get it by ID. Maybe that ID is the full URL, or maybe that ID is the config key, or the user ID. Once we have this data, the content of that data then can be serialized and deserialized according to the uses of that key. And at that point, does it matter if some of the keys are configuration data and some of them are user session data? Maybe not. Next up, time series databases. Time series databases are great for a lot of events. So if we have a machine producing a whole lot of events and we want to catalog those into time buckets, a time series database can be perfect. So we can create windows. Show me all of the things in 5 minutes, or break it into day buckets or month buckets. Now the cool thing here is these buckets, they can hold multiple values. When I'm looking at a traditional Excel type of experience, when I think of rows and columns, once I have a particular cell, it has a singular value. In a time series database, once I've defined those buckets, the cell has many values. So I can have a max value, I can have a min value, I can have an average value, I can count the values. These are possible in time series databases because of those time windowing functions. So time series databases, they're great for when I need that type of windowing, when I need those events. But they're not great for other things we've specifically optimized for that time windowing. They're great for IoT monitoring or real-time events from mobile devices or sensors. Stock trades would work really well because they're very time sensitive. When we have a lot of data where kind of the biggest unique thing is the time, the date, then we can start to speak to time series databases. Here's some example time series databases that can help you with your query to find others. Text search databases. These are focused on querying. We may pair them with a natural language processing engine so that we kind of think of them like a Google search engine, but we could just as easily have these for searching logs or searching other data. It's about creating an inverted index that allows us to query through that data. Given a keyword, find all the places in this document that have this keyword, or find all the documents that have this keyword. And so it's less about processing and joining and computation and more about just identifying the spots in the document and the particular documents. It's optimized for word-based search, and the schema is added at query time often, not always. On the downside, there aren't any relationships I can't join in this database. And it's really only good for text. That's kind of the purpose, is I'll go through a document, I'll identify all the words, and I'll index those. And that yields us stop words. Like and. These words don't have a whole lot of syntactic meaning in English, but in other languages we'll have different words. So stop words tend to be very cultural specific. Add to that, if I've decided that av is a stop word and is a stop word, well, what about the street named Avenue A? Well, both of those are stop words, so now the street has no name at all. Stop words, tuning stop words can be really problematic in text search databases. But perhaps if we combine these with natural language processing, we can create a methodology of, well, what did they mean by that? And to that end, maybe we don't key out stop words. Maybe we're looking for intent. And at that point, Avenue A is just fine. Next, so text search databases. Here are some examples of text search databases, and there are definitely many more. A lot of them are based on Lucene, which is pretty cool. They're best used for finding the location of particular words in a document, or finding which documents have matching words. Next up, object or blob stores, file systems. We can think of these roughly like a file system, and we may even use these for file systems. The key is often the path. We may invent folders by putting, slashes in the key, but ultimately it's just a key. And then the blob is a big binary blob. So these are great for very large things, videos, log files, backups, but they're not great for querying by value. Similar to a key value store, I would need to load up each one and deserialize it in a way that makes sense and see if that one matches. So for example, if I'm storing my backups up on S3 and I want to see, is this file in the backup? Well, I need to probably untar each backup file, and I need to have downloaded each backup file to do it. So basically I'm downloading the entire bucket to try and see if this file is in any of these backups. So I may choose to pair an object store with another type of store so that I have that metadata stored maybe in a SQL database or maybe in a NoSQL database that allows me to query it more richly. And then once I've found that by ID, now I go to that object blob and dig in. Amazon S3 is definitely the quintessential example here, but there are other object stores, and you could even use a NAS or a file system for this as well. They're great for big things that need storing, but not random access within those things. Next up, column stores. Now, column stores are a great adaptation of relational databases that allows data to be stored in columns instead of in rows. So in a traditional SQL database here on the left, we have rows, and we'll have columns, but for the most part, that row is stored together. And so now that that row is stored together, if I'm moving data within that row, like changing a null column to non-null, I may need to move that entire row on disk. By comparison, if I store it like in columns here on the right, then when the column changes, or then I can start to group things by column. So for example, if I'm grouping by country or maybe state, then there's only so many states in the Union or only so many countries on the planet. And so I can start to compress that data a lot better. Now I will have those other pointers to the other data associated with this data, so it's not just the column. But if we squint real hard, we could think of a column database maybe as an index in a SQL database. Maybe? It isn't a great analogy, but we can start to wrap our head around it with that. So the cool thing with column indexes is they get really compressed. There's only a couple of dozen states, so I only have a couple of dozen unique values in this column. So I can quickly seek to the spot in that column store, and then I can bulk read all the data associated with that. Column stores are great for sequencing into the thing that I like, and then bulk reading that data. By comparison, row stores are great for more of that random read and write. I get much better compression in a column store, but it's slower to seek. So column stores can be really good for analytics. So there you go. Analytics is great on a column store. Here's some column stores that work out really well. So next up, NewSQL databases. NewSQL databases are really an interesting category. We could think of these as like HTAP databases, or there are some other interesting names for these. NewSQL databases are SQL, but also partitioned. Now we saw that a partitioned mechanism like this in NoSQL databases. We had lots of little commodity hardware accomplishing this. With a NewSQL database, we have that, but we still have ACID compliance. So for example, in this example, we have aggregators that accept user queries. An aggregator will then publish that query to each leaf node that needs to participate in this query. And each leaf node will reach into the partitions where that data is stored, harvest the matching results, and return that back to the aggregator to create deterministic results. This allows us to scale up our database by scaling horizontally, adding more hardware, rather than just buying a bigger and bigger, beefier box. We could think of this as SQL, but with an SLA, because to get more performance, we add more machines instead of one bigger machine. NewSQL can be really, really helpful because it is much cheaper to scale. On the downside, there are more moving parts. So, for example, if I need to join data, I may need to move data across the nodes across the network between my leaf nodes to be able to get that join to happen correctly. Now that's not a real deal breaker, because those machines are usually in the same data center, probably in the same region, and so that network latency is specifically controlled. Yet I still have that great hardware redundancy, and so if I lose a particular piece of hardware, that's no big deal. I can replace that easily, and the database stays online the entire time. Here's some examples of NewSQL databases. It's great for when you outgrow your SQL database, when you want a relational database, but you don't want that spinning wheel on your dashboard or on your application. If you have too much data to fit in your database, or you need more users, or you need faster response times, then that's a good indication that it's time to start looking for a new SQL database. Hybrid databases. As we go looking at databases, we may notice that, well, my database is mostly this, but it also has that. In cases where we end up with the one big monolithic database, we're probably reaching for a hybrid database so that it can, oh, by the way, kind of start to do the other things that we need to. Hybrid databases, perhaps it's a SQL database, but it has a JSON column type, so we can treat it like a NoSQL database too. Or perhaps it has time series windowing functions, and everything else about it is a SQL database. Perhaps we have two column types. Perhaps we create a two-column table with one key and one big value, and call that a key value store. Perhaps we have row store and column store in the same database. These are indications that our database is a hybrid database. And for the most part, a lot of the databases that we've looked at are hybrid databases. I've categorized them this way because, well, that's pretty much where their strengths lie, but everyone's trying to be a little everything right now. So hybrid databases. Here's the money shot. Take out your phone and take a picture of this one, because this is the summary of all of the database types that we looked at today. We looked at relational, document, graph, key value, time series, text search, object, column store, and NewSQL. Here's kind of a single word description of what it is and what it might be good for. We looked at architectures, the monolithic on the one side and microdatabases on the other side. When we're forced into a monolithic database in spite of our microservices, we can reach for bounded context to start separating that database into manageable pieces. And then when we're at the point where we have enough automation to ensure that our databases are backed up and authenticated correctly, we can move to microdatabases, where we're much freer on our choice of vendors and database types. We can pick the database type that exactly matches our needs. As we look at microdatabases, they don't all need to be the same type, so we can choose the correct database for the task at hand. And perhaps our microservice needs more than one database. Maybe we need an object store, but we also need to have an index around the metadata, so we'll have a relational or a document store around that. Perhaps we need a caching tier in our microservice, so we'll have a key value store in addition to the relational store that produces that data. Perhaps we've reached the end of our capacity in our SQL database and we need to upgrade to a new SQL database to get at the more performance. And with event sourcing, we can publish events between microservices so that each database can get the data that it needs. Here's another money shot. Grab your phone and take a picture of this one. Here's my recommendations for when to choose what. Ideally, you're using database as a service. If you use database as a service, all of those pieces like, well, can you back this up? And is it backed up? And can you restore to this point in time? All of that is handled by your database vendor. And you get to sleep at night. That's really nice. You've outsourced uptime. That's perfect. If you end up with more than one database, if you get outside the monolithic database into microdatabases, then use automation as much as possible to ensure that you get authentication and you subscribe to backups for each of those microdatabases. My recommendation is to choose SQL database by default. The ACID compliance and the compatibility of the SQL query engine is really key in making you productive. If you have specific needs that match other things, then definitely stray into the other types to find the particular type that exactly matches that need. If you don't have a specific fit for that, then you probably want to look for a SQL database or a hybrid database that has enough of the pieces that you need to be able to accomplish the task. This has been a lot of fun getting to present here at Couchbase Online. Find me in that spot where the conference is organized, questions and answers. Or if you're watching this video later, hit me up on Twitter at rob_rich and grab these slides at robrich.org where you can also send me an email. Thanks for joining us.